In the vast silence of the cosmos, a faint signal once reached Earth, a whisper from the depths of space that scientists are still struggling to decode. What could it mean? Are we alone, or is this a glimpse of something far beyond our understanding? The universe is full of mysteries, and every discovery we make peels back another layer of its infinite complexity. Today, we're diving into 25 groundbreaking revelations that have reshaped how we see the cosmos, from enigmatic black holes to cosmic phenomena that defy explanation. These discoveries aren't just scientific milestones, they're keys to understanding our place in the universe and the incredible potential of human curiosity and innovation. Join us as we journey through the wonders of deep space, where every finding challenges what we thought we knew and opens doors to possibilities we've only begun to imagine. This is more than a story of stars and galaxies. It's a testament to humanity's relentless quest to explore the unknown, ready to see the universe in a whole new light. Let's begin. In September 2015, scientists made a discovery that shook the foundations of physics literally. For the first time in history, humanity detected gravitational waves, ripples in the fabric of spacetime itself. These waves were created by the collision of two black holes over 1 billion years ago, an event so cataclysmic that it sent vibrations across the cosmos, finally reaching Earth. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was the instrument that captured this monumental signal. It wasn't just a scientific achievement, it was a validation of Albert Einstein's prediction from a century earlier, proving that gravity could ripple through space and time like waves on a pond. The significance of this discovery cannot be overstated. Before LIGO detection, our understanding of the universe relied almost entirely on light, visible, infrared, X-rays, and radio waves. Gravitational waves opened an entirely new way to observe the cosmos, allowing us to listen to the universe in a way we never could before. Imagine being able to hear the distant echoes of black holes merging, neutron stars colliding, or even the faint whispers of the Big Bang itself. This breakthrough has given scientists a new tool to explore the most violent and energetic events in the universe, events that were previously hidden from view. Kip Thorne, one of the key figures behind LIGO, described the detection as the beginning of a new era in astronomy. And he was right. Since that first detection, gravitational wave astronomy has exploded, with dozens of events now recorded, each one offering new insights into the nature of black holes, neutron stars, and the very fabric of spacetime. But this is just the beginning. Gravitational waves have unlocked a new dimension of exploration, one that promises to reveal even more about the cosmos, and perhaps even the origins of the universe itself. As we move forward, these ripples in spacetime may guide us to discoveries we can't yet imagine, opening doors to realms of physics that remain mysteries. From the ripples of spacetime, we now turn to a phenomenon that flashes across the cosmos in the blink of an eye: fast radio bursts, or FRB. These are incredibly brief but extraordinarily powerful bursts of radio waves that originate from galaxies billions of light years away. Lasting just milliseconds, an FRB can release as much energy as the Sun does in 80 years. Picture this: a single, fleeting pulse of energy, so intense that it outshines entire galaxies for a fraction of a second. It's like a cosmic flashbulb going off in the depths of space, and scientists are racing to figure out what could possibly cause such an event. The origins of FRBs remain one of the most tantalizing mysteries in modern astronomy. Some theories suggest they come from highly magnetized neutron stars, known as magnetars, which are capable of producing immense bursts of energy. Others have proposed more exotic explanations, such as colliding black holes or even the speculative possibility of advanced extraterrestrial civilizations attempting to communicate. While the idea of alien signals captures the imagination, most researchers lean toward natural astrophysical processes, though the exact mechanism is still hotly debated. What makes FRBs so challenging to study is their unpredictability. These bursts are fleeting, appearing without warning and vanishing just as quickly, leaving scientists scrambling to catch them in action. Recent advancements in radio telescopes have begun to shed light on these enigmatic signals. In 2020, astronomers detected the first FRB originating from within our own galaxy, providing a closer look at what might be happening. This discovery pointed to Magnetars as the likely culprit, but the story is far from complete. Each new detection adds a piece to the puzzle, yet the full picture remains elusive. The sheer power and brevity of FRBs make them not only fascinating but also incredibly difficult to study. They require precise timing, sophisticated technology, and a bit of cosmic luck to observe. Imagine trying to solve a mystery where the clues disappear almost as soon as they appear. That's the challenge scientists face with FRBs. Yet, every burst they capture brings us closer to understanding the extreme conditions that produce them. These flashes of energy are more than just cosmic curiosities. They're windows into the most violent and energetic processes in the universe. As we continue to unravel their secrets, FRBs may reveal new insights into the nature of matter, the behavior of neutron stars, and even the structure of the universe itself. And speaking of cosmic mysteries, our next discovery takes us deeper into the heart of another enigmatic phenomenon, one that stretches the very fabric of reality itself. Now, let's shift our gaze to a cosmic tug-of-war that has left scientists both fascinated and baffled. Imagine the universe as a vast, interconnected web of galaxies, all moving under the influence of gravity. But what if something unseen, something colossal, was pulling entire clusters of galaxies in a specific direction? This is the mystery of the Great Attractor, a gravitational anomaly located roughly 250 million light-years from Earth. It's as if the universe has a hidden hand guiding galaxies toward an invisible point in space, and we're only beginning to understand its full significance. The Great Attractor isn't just a single object. It's a region of space with an immense concentration of mass, so powerful that it bends the paths of galaxies around it. Picture a giant whirlpool in the ocean, drawing everything nearby into its swirling currents. Galaxies, including our own Milky Way, are being pulled toward this cosmic vortex at speeds of millions of miles per hour. But here's the twist: we can't see what's causing this pull. The region lies behind the plane of our galaxy, obscured by dust and stars, making it one of the most elusive mysteries in modern astronomy. Adding to the intrigue is the concept of dark flow, a phenomenon where clusters of galaxies appear to be moving in a uniform direction, far beyond the influence of the Great Attractor. This motion defies our current understanding of the universe's expansion, which is driven by dark energy. Think of it like this: if the universe is an expanding balloon, galaxies should be moving apart in all directions. But dark flow suggests that some unseen force is tugging these galaxies in a specific direction, as if the balloon itself is being pulled by an invisible hand. Scientists have proposed that this motion could be caused by massive structures outside our observable universe, regions so distant and dense that their gravitational influence reaches across unimaginable distances. What does this mean for our understanding of the cosmos? The Great Attractor and dark flow challenge the very foundations of cosmology. They hint that there's more to the universe than what we can observe: more mass, more structure, and perhaps even more dimensions. Some researchers speculate that these phenomena could be evidence of other universes beyond our own, exerting a gravitational pull on our cosmic neighborhood. While this idea remains speculative, it opens the door to questions about the true nature of reality and the limits of our knowledge. To put it simply, the Great Attractor and dark flow are like cosmic breadcrumbs leading us toward deeper mysteries. They remind us that the universe is far stranger and more complex than we've ever imagined. And as we continue to explore these forces, we may uncover not just answers, but entirely new questions about the fabric of existence. This is the beauty of astronomy. Every discovery peels back another layer, revealing a universe that's endlessly surprising and profoundly mysterious. But the cosmos doesn't stop at gravitational anomalies. Beyond the Great Attractor lies another enigma, one that blurs the line between science and speculation, a phenomenon so bizarre that it challenges our very understanding of time and space. In October 2017, astronomers spotted something extraordinary, a visitor from beyond our solar system, named Oumuamua, a Hawaiian word meaning scout or messenger. This mysterious object was the first confirmed interstellar traveler ever observed passing through our cosmic neighborhood. Unlike anything we'd seen before, Oumuamua was a cosmic enigma, sparking debates, theories, and even a touch of cosmic wonder. What made this object so unusual? For starters, it had a peculiar shape, elongated, almost like a cigar or a pancake, unlike the typical asteroids or comets we're used to seeing. Its trajectory was equally strange, speeding through the solar system at an angle that defied the usual paths of objects orbiting the Sun. The discovery of Oumuamua ignited a firestorm of scientific curiosity and speculation. Was it a simple asteroid ejected from another star system, or something far more intriguing? Some researchers suggested it might be a comet, but one without the usual tail of gas and dust. Others proposed it could be a fragment of a shattered planet, a cosmic shard flung across the galaxy by some ancient cataclysm. Then came the more provocative idea: could Oumuamua be an alien spacecraft? The notion wasn't entirely science fiction. Its unusual acceleration as it moved away from the Sun, which couldn't be fully explained by gravity alone, fueled imaginations and headlines. Could this be a probe sent by an advanced civilization, perhaps even equipped with some form of technology? Astronomers like Karen Meach, who led the team studying Oumuamua, worked tirelessly to piece together clues about this interstellar visitor. What they found was both fascinating and frustrating. Oumuamua's surface appeared reddish, suggesting it had been exposed to cosmic radiation for millions, if not billions, of years. Yet, its true nature remained elusive. The object was too faint and distant to capture detailed images, leaving scientists to rely on indirect observations and educated guesses. This lack of definitive data highlighted the challenges of studying interstellar objects. They're fleeting, unpredictable, and often vanish before we can fully understand them. The debate over Oumuamua's identity also underscored the scientific process at its best. Every hypothesis was examined, tested, and refined as new data emerged. While the alien spacecraft theory captured public imagination, most astronomers leaned toward natural explanations, such as outgassing, a process where trapped gases escaping from the object could have provided the slight push that altered its trajectory. Still, the sheer mystery of Oumuamua reminded us how much we still have to learn about the universe. Its brief visit was a cosmic wake-up call, showing that our solar system isn't an isolated bubble but part of a much larger, interconnected galactic neighborhood. Oumuamua's journey through our solar system may have been fleeting, but its impact on astronomy was profound. It taught us to expect the unexpected and to keep our instruments ready for the next interstellar visitor. Already, a second interstellar object named Borisov has been detected, offering another glimpse into the diversity of objects drifting between the stars. What else might be out there waiting to be discovered? The possibilities are as vast as the cosmos itself, and each new find brings us closer to understanding the grand tapestry of the universe. As we continue to explore, we're reminded that the cosmos is full of surprises, and some of the greatest discoveries may come from the most unexpected places. And speaking of cosmic surprises, our next discovery takes us even further into the unknown, to a phenomenon so strange that it challenges everything we thought we knew about the nature of reality itself. In December of 1995, the Hubble Space Telescope did something extraordinary. It pointed its lens at a seemingly empty patch of sky, no larger than a grain of sand held at arm's length. What it revealed would forever change how we see the universe. This tiny, unremarkable slice of space contained not emptiness, but a breathtaking tapestry of light thousands of galaxies, each one a swirling island of stars, dust, and gas. This image, known as the Hubble Deep Field, was more than just a photograph. It was a cosmic revelation, a window into the vastness of the universe that left scientists and the public alike in awe. Before the Hubble Deep Field, our understanding of the cosmos was limited. We knew galaxies existed, but we had no idea just how many were out there. The image showed galaxies of all shapes and sizes, spirals, ellipticals, and irregular blobs, each one a testament to the diversity of the universe. Some of these galaxies were so far away that their light had traveled for over 13 billion years to reach us, offering a glimpse into the early universe. It was like finding a treasure trove of ancient artifacts, each one telling a story of how the universe evolved over billions of years. The technological marvel behind this image cannot be overstated. Hubble's ability to capture such faint light over long exposure times was a triumph of engineering and innovation. By focusing on this one tiny region for 10 consecutive days, Hubble collected enough light to reveal the faintest and most distant objects ever observed. This achievement was a testament to human ingenuity, proving that even the smallest patch of sky could hold infinite wonders if we had the patience and tools to look closely enough. But the Hubble Deep Field wasn't just a scientific milestone, it was a philosophical one. It forced us to confront the sheer scale of the universe and our place within it. Seeing thousands of galaxies in such a small area suggested that the universe might contain hundreds of billions of galaxies, each with billions of stars. Suddenly, the idea of being alone in the cosmos seemed almost absurd. The image sparked a sense of humility and wonder, reminding us that the universe is far larger and more complex than we could ever fully comprehend. The Hubble Deep Field also raised profound questions about the nature of existence. How did these galaxies form? What processes shaped their evolution? And what does it mean for humanity to exist in such a vast and ancient cosmos? These questions continue to drive scientific inquiry, pushing us to build even more advanced telescopes and explore deeper into the universe's history. As we marvel at the Hubble Deep Field, it's worth considering what lies beyond the edges of that iconic image. What other secrets does the universe hold waiting to be uncovered? The next discovery takes us from the grand scale of galaxies to the intimate lives of stars, how they are born, live, and die, shaping the cosmos in ways we're only beginning to understand. This journey through the life cycles of stars will reveal not just the mechanics of the universe, but the stories of the celestial objects that light up the night sky and make the cosmos the awe-inspiring place it is. In February of 1987, astronomers around the world witnessed an event so rare and spectacular that it became a landmark in the study of the cosmos. Supernova 1987, A or SN 1987 for short, erupted in the Large Magellanic Cloud, a neighboring galaxy to our Milky Way. This wasn't just any stellar explosion, it was the closest supernova observed in nearly 4 centuries, and it gave scientists a front-row seat to one of the universe's most dramatic processes, the death of a massive star and the birth of something extraordinary in its wake. The star that became SN 1987 was a blue supergiant, a colossal object 20 times more massive than our Sun. When it ran out of fuel, its core collapsed under its own gravity, triggering a cataclysmic explosion so bright that it outshone entire galaxies. For months, the supernova was visible to the naked eye, even from Earth, a dazzling reminder of the universe's raw power. But the real treasure wasn't the light show, it was the wealth of data that followed. For the first time, scientists could study a supernova in unprecedented detail, from the initial shockwave to the formation of its glowing remnants. One of the most significant revelations from SN 1987 was the confirmation of how neutron stars form. When the star's core collapsed, it didn't just explode outward, it crushed itself into an ultra-dense object, a neutron star, with a mass greater than the Sun packed into a sphere no wider than a city. This was a monumental discovery, as it provided direct evidence for a theoretical process that had only been speculated about before. Neutron stars, with their mind-bending density and intense magnetic fields, are among the most extreme objects in the universe, and SN 1987 gave us our clearest glimpse yet into their birth. But the supernova did more than just reveal the origins of neutron stars. It also showed us how the elements that make up our world are forged in the hearts of dying stars. During the explosion, conditions became so extreme that atoms were fused together, creating heavy elements like gold, silver, and uranium. These elements were then scattered into space, seeding the cosmos with the building blocks of planets and even life itself. In a very real sense, the iron in your blood and the calcium in your bones were born in explosions like SN 1987A. It's a humbling thought. We are all made of stardust, the remnants of ancient cosmic events. The story of SN 1987 is also a testament to the dedication of astronomers who raced to capture every detail of the event. From telescopes in Chile to detectors buried deep underground, scientists around the globe worked tirelessly to collect data. One of the most remarkable aspects of their work was the detection of neutrinos, tiny, nearly massless particles that flooded out of the collapsing core hours before the supernova's light reached Earth. These ghostly particles offered a sneak peek into the star's final moments, confirming theoretical predictions and opening new avenues for research. It was a global effort, a collaboration that transcended borders and united humanity in the pursuit of knowledge. Today, the remnants of SN 1987 continue to fascinate scientists. The glowing ring of gas left behind by the explosion is a cosmic laboratory, offering clues about how supernovas shape the universe. It's a reminder that even in destruction, there is creation, new stars, new planets, and new possibilities. And as we study these remnants, we're reminded that the universe is a dynamic, ever-changing place where even the most violent events can lead to the birth of something extraordinary. As we turn our attention from the birth of neutron stars, we find ourselves drawn to the lingering echoes of such cosmic explosions, remnants that tell stories of destruction, rebirth, and the enduring legacy of the stars. But what happens when a star doesn't just collapse but vanishes entirely, leaving behind a shadow in the fabric of space? That's where our next discovery takes us, into the enigmatic world of black holes. Among the most intriguing objects in the cosmos are pulsars, rapidly spinning neutron stars that act like cosmic lighthouses, sending out beams of radiation with astonishing regularity. These celestial objects were first discovered in 1967 by astrophysicist Jocelyn Bell Burnell, who noticed a series of strange, repeating signals coming from deep space. At the time, the signals were so precise and rhythmic that they sparked wild speculation. Could these be messages from an alien civilization? The idea captured imaginations, but the truth turned out to be even more fascinating. What Bell-Burnell had stumbled upon was a pulsar, a neutron star spinning at incredible speeds, sometimes hundreds of times per second. As it rotates, it emits beams of radiation from its magnetic poles. When these beams sweep across Earth, we detect them as pulses of energy, hence the name pulsar. Imagine a lighthouse on a distant shore, its light flashing rhythmically as it spins. That's essentially what a pulsar does, only on a cosmic scale, with beams of radio waves, X-rays, or even gamma rays instead of visible light. The discovery of pulsars was a game-changer for astronomy. These objects are not just curiosities, they're laboratories for testing some of the most fundamental theories in physics, including Einstein's theory of general relativity. Because pulsars are so dense and their rotation so precise, they provide a unique way to study the effects of gravity in extreme conditions. For example, when a pulsar orbits another dense object, like a black hole or another neutron star, the resulting gravitational interactions can subtly alter the timing of its pulses. These changes allow scientists to measure the properties of spacetime itself, offering insights into how gravity shapes the universe. Pulsars also play a crucial role in mapping the cosmos. Their steady pulses act like cosmic clocks, helping astronomers measure distances across the galaxy and even detect gravitational waves. In fact, the first indirect evidence for gravitational waves came from observations of a pulsar in a binary system, where the gradual decay of its orbit matched Einstein's predictions perfectly. This discovery earned the researchers involved a Nobel Prize and cemented pulsars as indispensable tools for exploring the universe. But pulsars aren't just scientific instruments, they're also windows into the lives of stars. These objects are born from the explosive deaths of massive stars, their cores collapsing into ultra-dense neutron stars that retain the original star's rotation and magnetic field. Over time, pulsars slow down and fade, but their legacy endures, shaping the cosmos around them. Some pulsars even emit enough energy to power entire nebulae, lighting up regions of space with their brilliance. Jocelyn Bell Burnell's discovery was a reminder that the universe is full of surprises, often hiding in plain sight. What began as a mysterious signal turned out to be a beacon of knowledge, shedding light on the nature of gravity, the life cycles of stars, and the vastness of space. Pulsars are testament to the fact that even the most fleeting signals can lead to profound discoveries, challenging our understanding of the cosmos and inspiring us to look deeper. As we move from the rhythmic pulses of neutron stars, we find ourselves drawn to another cosmic mystery, one that exists at the very edge of our understanding, where the laws of physics as we know them begin to break down. This is the realm of black holes, objects so dense and powerful that they warp the very fabric of reality. But before we dive into their shadowy depths, let's take a moment to appreciate how pulsars have illuminated our path, guiding us toward the next frontier of discovery. Now let's step back in time, way back to the very beginning of the universe itself. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, made a discovery so profound that it fundamentally changed our understanding of the cosmos. While working at Bell Labs in New Jersey, they stumbled upon a faint, persistent hum of microwave radiation coming from every direction in the sky. At first, they thought it might be interference, perhaps from pigeons nesting in their antenna. But after months of meticulous investigation, they realized they'd found something far more significant. This was the cosmic microwave background radiation, or CMB, the faint afterglow of the Big Bang. The CMB is often described as the oldest light in the universe, a snapshot of what the cosmos looked like just 380,000 years after the Big Bang. Before this point, the universe was too hot and dense for light to travel freely. It was a seething soup of particles and energy. But as the universe expanded and cooled, protons and electrons combined to form neutral atoms, allowing light to break free and travel across space. This light, stretched by the expansion of the universe over billions of years, now reaches us as microwaves, a faint whisper from the dawn of time. The discovery of the CMB was a monumental achievement, earning Penzias and Wilson the Nobel Prize in Physics. It provided the strongest evidence yet for the Big Bang theory, confirming that the universe had a definite beginning and has been expanding ever since. But the CMB isn't just a relic of the past, it's a treasure trove of information about the early universe. Embedded within its faint glow are tiny fluctuations in temperature, variations as small as 1 part in 100,000. These irregularities are the seeds of cosmic structure, the blueprint for the galaxies, stars, and planets that would later form. Experiments like the Cosmic Background Explorer, or COBE, and later the Planck satellite, have mapped these fluctuations in exquisite detail, revealing a universe that was remarkably smooth but not perfectly uniform. These slight differences in density and temperature were the gravitational seeds that, over billions of years, grew into the vast cosmic web we see today. Without these tiny imperfections, the universe might have remained a featureless expanse, devoid of the structures that make it so rich and dynamic. The CMB also offers clues about the composition of the universe. By analyzing its properties, scientists have determined that ordinary matter, the stuff that makes up stars, planets, and us, makes up just 5% of the universe. The rest is a mysterious mix of dark matter and dark energy, two enigmatic components that dominate the cosmos but remain poorly understood. In this way, the CMB is not just a window into the past but also a guide to the universe's hidden architecture. What's truly remarkable about the CMB is how it connects us to the very origins of existence. When we look at its faint glow, we're seeing the universe as it was in its infancy, a time before galaxies, stars, or even atoms as we know them. It's a humbling reminder of our place in the cosmos and the incredible journey that led from a hot, dense beginning to the complex, beautiful universe we inhabit today. As we reflect on this cosmic echo, we're reminded that the universe is still expanding, carrying galaxies farther apart with each passing moment. And that brings us to our next discovery, one that reveals not just how the universe began, but how it continues to grow, evolve, and shape the destiny of everything within it. In the late 1990s, astronomers made a discovery that turned our understanding of the cosmos on its head. They found that not only is the universe expanding, but that expansion is speeding up, accelerating faster and faster as time goes on. This revelation was so groundbreaking that it earned the researchers involved the Nobel Prize in Physics, and it introduced us to one of the greatest mysteries in modern science, dark energy. But how did we come to this astonishing conclusion, and what does it mean for the fate of the universe? The answers lie in the light of dying stars halfway across the cosmos. The key to this discovery was a specific type of supernova known as a Type 1a supernova. These stellar explosions are so consistent in their brightness that they're often referred to as standard candles. By measuring how bright these supernovae appear from Earth, scientists can calculate their distance. But when two independent teams of astronomers began studying these distant explosions in the late 1990s, they noticed something strange. The supernovae were fainter than they should have been, meaning they were farther away than expected. This could only mean one thing: the space between us and those supernovae was stretching faster than anyone had predicted. The universe wasn't just expanding, it was accelerating. This discovery was a shock. For decades, scientists had assumed that the expansion of the universe, set in motion by the Big Bang, would slow over time due to the pull of gravity. Instead, the opposite was happening. Something was counteracting gravity, pushing galaxies apart at an ever-increasing rate. This mysterious force was dubbed dark energy, and it's now believed to make up about 70% of the universe's total energy content. Yet, despite its dominance, dark energy remains one of the most elusive concepts in physics. We know it's there, but we have no idea what it actually is. The implications of this accelerating expansion are profound. If dark energy continues to drive the universe apart at this rate, the future of the cosmos could be a cold and lonely one. Galaxies will drift farther and farther apart, stars will burn out, and over trillions of years, the universe may become a vast, empty expanse. It's a stark contrast to earlier theories that suggested the universe might eventually collapse back in on itself. Now it seems the fate of the cosmos is not a fiery crunch but a slow, silent fade. But the story doesn't end there. Dark energy has opened up a whole new frontier of research. Scientists are now using powerful telescopes and satellites to study the universe's expansion in even greater detail, searching for clues about the nature of dark energy. Is it a property of space itself, as Einstein once proposed with his cosmological constant? Or is it something entirely new, a force we've yet to fully comprehend? Every observation brings us closer to answering these questions, but for now, dark energy remains one of the greatest puzzles in science. As we grapple with the mysteries of dark energy, it's worth reflecting on how far we've come. Just a century ago, we didn't even know the universe was expanding. Now, we're peering into the very fabric of reality, trying to understand the forces that shape its destiny. And while dark energy may remain shrouded in mystery, its discovery reminds us that the universe is full of surprises, waiting to be uncovered by those who dare to look. From the enigmatic force driving the universe apart, we now turn our attention to the very building blocks of existence, the particles and forces that make up everything we see and even the things we can't. This next discovery takes us into the quantum realm, where the rules of physics as we know them begin to blur, and where the smallest particles hold the keys to the universe's greatest secrets. In the world of particle physics, there's one discovery that stands as a crowning achievement of human ingenuity and collaboration, a discovery that answered one of the most profound questions in science: why does anything have mass at all? This is the story of the Higgs boson, a particle so elusive that it took decades of theoretical work, cutting-edge technology, and the combined efforts of thousands of scientists to finally reveal its existence. In July of 2012, researchers at CERN Large Hadron Collider announced they had found it, a moment that sent ripples through the scientific community and beyond. The Higgs boson is often called the God particle, a nickname that, while dramatic, undersells its true significance. In reality, it's the key to understanding how particles acquire mass, a fundamental property that shapes the very fabric of our universe. Without mass, particles would zip through space at the speed of light, never forming atoms, molecules, or the complex structures that make up everything we see. The Higgs boson is the linchpin of the standard model of particle physics, a theory that describes the fundamental particles and forces that govern the universe. Its discovery was the final piece of that puzzle, confirming a framework that had been decades in the making. But finding the Higgs boson was no small feat. The Large Hadron Collider, or LHC, is the most powerful particle accelerator ever built, a 17-mile-long ring buried beneath the French-Swiss border. Inside this colossal machine, protons are accelerated to nearly the speed of light and smashed together, recreating conditions similar to those just moments after the Big Bang. It's like a cosmic microscope, allowing scientists to peer into the subatomic world and search for particles that exist for only the tiniest fraction of a second. The Higgs boson is one such particle, and detecting it required a level of precision and innovation that pushed the boundaries of what was thought possible. The discovery wasn't just a triumph of technology, it was a testament to the power of collaboration. Thousands of scientists from over 100 countries worked together on the LHC experiments, analyzing mountains of data to identify the faint signals of the Higgs boson amidst the chaos of particle collisions. When the announcement came, it was met with global celebration, a moment that united the scientific community and captured the imagination of the public. Peter Higgs, the physicist who first predicted the particle's existence in the 1960s, was in the audience that day, witnessing the culmination of a lifetime's work. The implications of this discovery are far-reaching. The Higgs boson not only completes the standard model, but also opens new doors for exploration. It raises questions about the nature of mass, the possibility of extra dimensions, and the mysteries of dark matter. Some theories suggest that the Higgs field, the invisible energy field associated with the boson, could hold clues about the early universe and the forces that shaped its evolution. As we continue to study this remarkable particle, we may uncover insights that reshape our understanding of reality itself. The discovery of the Higgs boson reminds us that the universe is governed by elegant, underlying principles, waiting to be uncovered by those who dare to ask the big questions. It's a story of curiosity, perseverance, and the relentless pursuit of knowledge. A story that continues to inspire us as we explore the deepest mysteries of existence. And now, as we turn our gaze from the tiniest particles to the grandest structures, we find ourselves exploring another cosmic marvel, one that connects the smallest building blocks of matter to the vast web of galaxies that stretch across the universe. This next discovery takes us into the realm of the cosmic web, where the universe's largest structures reveal the hidden architecture of existence. Imagine the universe as a colossal tapestry, woven from threads of galaxies, gas, and dark matter, stretching across billions of light years. This is the cosmic web, a vast, intricate network that forms the backbone of the cosmos. It's not just a random scattering of stars and galaxies. It's a structured, almost architectural framework that connects everything in the universe. From the densest clusters of galaxies to the emptiest voids, the cosmic web is a map of the universe's evolution, revealing how gravity has shaped the cosmos over billions of years. For decades, astronomers have worked to piece together this grand structure. Early observations of galaxies showed that they weren't distributed evenly across the sky. Instead, they seemed to cluster together, forming filaments and walls that surrounded enormous, empty regions called voids. It was as if the universe had a skeleton, a hidden framework that dictated where galaxies would form and how they would move. But mapping this skeleton was no easy task. The cosmic web is vast, spanning distances so immense that even light takes billions of years to traverse them. To understand it, scientists turn to both observations and simulations, creating models that could replicate the universe's growth from its earliest moments. One of the key tools in this effort has been computer simulations, which use the laws of physics to recreate the universe's evolution. By inputting data about dark matter, dark energy, and the initial conditions of the cosmos, these simulations can predict how structures like the cosmic web form. The results are astonishingly accurate, matching what we observe in the real universe. These virtual universes show how dark matter, an invisible substance that makes up most of the universe's mass, acts as the scaffolding for the cosmic web. Over billions of years, gravity pulls dark matter into dense filaments, with galaxies forming along these threads like beads on a string. But simulations are only part of the story. Observational astronomy has also played a crucial role in revealing the cosmic web. Powerful telescopes like the Hubble Space Telescope and the Sloan Digital Sky Survey have captured images of galaxy clusters and filaments, allowing scientists to trace the web's structure. More recently, techniques like gravitational lensing, where the gravity of massive objects bends light from distant galaxies, have provided even more detailed maps. These observations confirm that the cosmic web is not just a theoretical construct. It's a real, physical feature of the universe. The cosmic web isn't just a static structure, it's a dynamic, evolving system. Galaxies move along its filaments, pulled by gravity toward dense clusters, while gas flows through the web, feeding the growth of galaxies and stars. This constant motion shapes the universe's history, influencing how galaxies form, evolve, and interact. Without the cosmic web, the universe would be a very different place, a featureless expanse, devoid of the rich diversity we see today. Mapping the cosmic web is no small challenge. Its sheer scale and complexity make it one of the most ambitious projects in modern astronomy, but the effort is worth it. By understanding the web, we're not just mapping the universe's structure, we're uncovering its history, tracing the forces that shaped it from the Big Bang to the present day. It's a reminder that the universe is not just a collection of isolated objects, but a connected, interdependent system, a cosmic dance guided by gravity and shaped by time. As we marvel at the grandeur of the cosmic web, we're reminded that the universe is filled with extremes, environments so intense, so alien, that they push the boundaries of what we thought was possible. And it's to one of these extreme environments that we now turn, where the laws of physics as we know them are tested to their limits. In April of 2019, humanity achieved something once thought impossible. We captured an image of a black hole. This historic moment, made possible by the Event Horizon Telescope, or EIT, was more than just a scientific triumph. It was a glimpse into the heart of one of the universe's most mysterious and extreme environments. The image, a glowing ring of light surrounding a dark void, became an instant icon, a visual representation of the power and strangeness of black holes. But what does this image actually show, and how did we manage to photograph something that, by definition, traps light itself? The answers lie in a groundbreaking combination of technology, collaboration, and sheer determination. The EIT isn't a single telescope, but a global network of radio observatories spread across the globe. By synchronizing these telescopes and combining their data, scientists effectively created a virtual telescope the size of Earth itself. This extraordinary feat allowed them to capture the faint radio waves emitted by the superheated gas swirling around the black hole's event horizon, the point of no return where gravity becomes so strong that not even light can escape. The black hole in question, located at the center of the galaxy M87, is a supermassive monster weighing in at 6.5 billion times the mass of our Sun. Its sheer size and distance made it an ideal target for this unprecedented experiment. The image itself is a marvel of both science and art. The glowing ring is caused by light bending around the black hole's immense gravity, a phenomenon predicted by Einstein's theory of general relativity. The dark center is the shadow of the event horizon, a region where spacetime itself is warped beyond recognition. This shadow isn't just a void, it's a window into the extreme physics that govern black holes, a place where the laws of gravity and quantum mechanics collide in ways we don't yet fully understand. For scientists, the image was a treasure trove of data, confirming long-held theories about how black holes behave while also raising new questions. The implications of this discovery extend far beyond a single photograph. By studying black holes, we're probing the very fabric of spacetime, testing the limits of our understanding of the universe. Black holes are not just cosmic curiosities, they're laboratories for exploring the most fundamental questions in physics. How does gravity behave under such extreme conditions? What happens to matter as it crosses the event horizon? And what can black holes tell us about the origins and fate of the universe? The EIT's image has brought us closer to answering these questions, but it has also revealed how much we still have to learn. The success of the Event Horizon Telescope is a testament to the power of collaboration. Over 200 scientists from more than 60 institutions around the world worked together to make this image possible. a reminder that the greatest discoveries are often the result of collective effort. It's also a testament to human ingenuity, proving that even the most daunting challenges can be overcome with creativity and perseverance. The image of the black hole is more than just a scientific achievement. It's a symbol of what we can accomplish when we aim for the stars, or in this case, the darkest corners of the cosmos. As we marvel at this groundbreaking image, it's worth reflecting on what black holes represent. They are the ultimate expression of gravity's power, places where the rules of physics as we know them break down. Yet, they are also gateways to new understanding, offering clues about the nature of spacetime, the behavior of matter, and the evolution of the universe itself. And as we continue to study these enigmatic objects, we may uncover insights that reshape our understanding of reality. From the shadowy depths of black holes, we now turn to another cosmic phenomenon, one that unleashes unimaginable energy, lighting up the universe in ways that challenge our understanding of its most violent events. This next discovery takes us into the heart of the universe's most energetic explosions, where the forces at play are as mysterious as they are powerful. Among the most cataclysmic events in the cosmos are gamma-ray bursts, brief, intense flashes of energy that outshine entire galaxies for a few fleeting seconds. These bursts are the universe's most powerful explosions, releasing more energy in a single second than the Sun will emit over its entire 10 billion-year lifetime. But what causes these extraordinary events, and what can they tell us about the life and death of the universe's most massive stars? The answers lie in the violent deaths of stars known as hypernova and the secrets they hold about the extremes of cosmic evolution. Gamma-ray bursts, or GRB, were first detected in the 1960s by military satellites designed to monitor nuclear explosions on Earth. Instead, these satellites picked up bursts of gamma rays coming from deep space, sparking a mystery that would take decades to unravel. Today, we know that GRBs come in two main varieties: short bursts, which last less than 2 seconds, and long bursts, which can persist for several minutes. The long bursts, in particular, are linked to hypernova, the explosive deaths of stars many times more massive than our Sun. When such a star exhausts its fuel, its core collapses into a black hole or neutron star, triggering a massive explosion that ejects its outer layers into space. This explosion is so powerful that it produces a narrow, focused beam of gamma rays, which we detect as a GRB. Detecting these bursts is no easy task. GRBs are fleeting, often lasting just a few seconds, and they can come from any direction in the sky. To catch them, scientists rely on satellites like NASA's Swift and Fermi observatories, which scan the skies for sudden spikes in gamma-ray activity. Once a burst is detected, ground-based telescopes quickly swing into action, capturing the afterglow, a fading glow of light that lingers after the initial explosion. This afterglow provides crucial clues about the burst's origin, distance, and energy, helping scientists piece together the story of the star that created it. But GRBs aren't just cosmic fireworks, they're also windows into the early universe. Because they are so bright, they can be seen from billions of light years away, offering a glimpse into the universe's distant past. By studying the light from these bursts, scientists can learn about the conditions in the early universe, the formation of the first stars, and the evolution of galaxies. GRBs also provide a unique laboratory for testing the laws of physics under extreme conditions, from the behavior of matter near black holes to the limits of Einstein's theory of relativity. However, these bursts aren't just objects of scientific curiosity, they also pose a potential threat to life on Earth. If a GRB were to occur within a few thousand light years of our planet, the intense radiation could strip away the ozone layer, exposing life to harmful ultraviolet rays from the Sun. While the chances of such an event are low, the consequences would be catastrophic. Fortunately, the universe is vast and GRBs are rare, with only a few occurring in any given galaxy over millions of years. Still, their existence reminds us of the delicate balance that allows life to thrive on our planet. As scientists continue to study gamma-ray bursts and hypernova, they're uncovering new insights into the life cycles of stars, the structure of the universe, and the forces that shape it. These explosive events are not just endpoints, they're also beginnings, seeding the cosmos with the heavy elements that form planets, stars, and even life itself. And as we peer deeper into their origins, we're reminded of the incredible power and complexity of the universe. From the explosive deaths of stars, we now turn to a question that has captivated humanity for centuries. Are we alone in the universe? This next discovery takes us into the search for extraterrestrial life, where new technologies and bold ideas are pushing the boundaries of what we thought was possible. In the vast expanse of the cosmos, one of the most tantalizing discoveries in recent years has been the TRAPPIST-1 system, a planetary family located just 40 light-years from Earth. Named after the transiting planets and planetesimal small telescope in Chile that first identified it, this system is home to 7 Earth-sized planets orbiting a small, cool star known as a red dwarf. What makes this discovery so extraordinary is not just the number of planets, but the possibility that some of them could harbor liquid water, and perhaps even the conditions necessary for life. The TRAPPIST-1 planets are tightly packed around their star, with orbits so close that a year on some of them lasts just a few Earth days. Despite their proximity to the star, the cooler nature of red dwarfs means that several of these planets fall within the habitable zone, the region where temperatures could allow liquid water to exist on their surfaces. This has sparked excitement among astronomers, as liquid water is one of the key ingredients for life as we know it. Of the 7 planets, 3, TRAPPIST-1e, F, and G stand out as the most promising candidates for further study. Detecting these planets was no small feat. Scientists used a technique called the transit method, which involves observing the slight dimming of a star's light as a planet passes in front of it. This method has revolutionized the search for exoplanets, allowing astronomers to identify thousands of worlds beyond our solar system. In the case of TRAPPIST-1, the star's small size and the planet's close orbits made the dimming effect more pronounced, enabling researchers to detect and study them in remarkable detail. Advanced telescopes like NASA's Spitzer and Kepler space observatories played crucial roles in confirming the discovery and providing insights into the planet's properties. But studying these distant worlds comes with its own set of challenges. Red dwarf stars, while abundant in the universe, are known for their volatile activity, including frequent flares that could strip away a planet's atmosphere or bombard it with harmful radiation. This raises questions about the long-term habitability of the TRAPPIST-1 planets. Could they maintain stable atmospheres despite their star's temperamental behavior? And if so, what might those atmospheres look like? These are the kinds of questions that astronomers are now working to answer, using tools like the James Webb Space Telescope to analyze the planet's atmospheres for signs of water vapor, oxygen, or other potential markers of life. The TRAPPIST-1 system is more than just a collection of intriguing planets. It's a reminder of how diverse and dynamic the universe can be. Each discovery in this system brings us closer to understanding what makes a planet habitable and how common such worlds might be. It also fuels the larger quest to answer one of humanity's most profound questions. Are we alone in the universe? While we may not have definitive answers yet, the TRAPPIST-1 system offers a tantalizing glimpse of what might be possible, sparking our imagination and driving us to explore further. As we marvel at the possibilities of distant worlds, we now turn our attention to a discovery that takes us back to the very beginning, a glimpse of the universe's oldest light, a remnant of the Big Bang itself. This next discovery will reveal how the cosmos looked in its infancy and how it has evolved into the vast, intricate structure we see today. Deep within the constellation Libra, a faint, unassuming star holds a secret that has rewritten our understanding of the cosmos. Known as Methuselah, or HD 140283, this ancient star is estimated to be nearly 14 billion years old, almost as old as the universe itself. Its discovery has not only challenged our theories about stellar evolution, but also offered a rare glimpse into the conditions of the early universe, a time when the first stars were just beginning to ignite. Methuselah's age is nothing short of astonishing. For decades, scientists believed that stars older than 13 billion years were impossible, given the age of the universe itself, which is estimated to be around 13.8 billion years. Yet, Methuselah defies this expectation, existing as a living relic from the universe's infancy. This star is a survivor, a witness to the birth of galaxies, the formation of planets, and the slow march of cosmic time. Its very existence raises profound questions. How did a star form so soon after the Big Bang? And what does its longevity tell us about the early universe? Determining Methuselah's age was no simple task. Astronomers used a combination of techniques, including measuring its brightness, temperature, and chemical composition. One of the key clues came from its low levels of iron, a metal that was rare in the early universe. Stars that formed shortly after the Big Bang contain far less iron than younger stars, which have been enriched by the deaths of earlier generations. Methuselah's iron-poor composition pointed to an ancient origin, but it was the star's motion through space, its parallax and velocity, that helped refine its age even further. By tracing its path and comparing it to models of stellar evolution, scientists concluded that Methuselah is a true cosmic elder. The implications of this discovery are profound. Methuselah challenges our assumptions about how stars form and evolve, forcing us to reconsider the timeline of the early universe. If stars like Methuselah could form so soon after the Big Bang, it suggests that the conditions for star formation were more dynamic and varied than we once thought. It also raises questions about the nature of the first stars, giant, short-lived behemoths that seeded the cosmos with heavier elements. Methuselah may not be one of those first stars, but it's a close relative, offering a rare window into a time when the universe was young and untamed. This ancient star also has implications for cosmology. Its age aligns closely with the universe's estimated age, providing an independent check on our understanding of cosmic history. It's a reminder that the universe is full of surprises, and that even the faintest stars can hold clues to its deepest mysteries. Methuselah is more than just a cosmic curiosity. It's a testament to the resilience and complexity of the universe, a living link to the dawn of time. As we marvel at Methuselah's ancient light, we're reminded that the universe is filled with mysteries waiting to be uncovered. And one of the greatest of these mysteries lies in something we can't see, touch, or even fully understand, a substance that makes up most of the universe's mass yet remains invisible to us. This brings us to our next discovery, a journey into the enigmatic realm of dark matter. In the grand tapestry of the cosmos, there's a hidden thread, a mysterious substance that makes up most of the universe's mass, yet remains invisible to our eyes. This is dark matter, a cosmic enigma that has puzzled scientists for decades. But how do we know it exists if we can't see it? The answer lies in one of the most dramatic cosmic events ever observed, the collision of galaxy clusters in the Bullet Cluster. This extraordinary event didn't just provide evidence for dark matter. It revealed its presence in a way that was as clear as it was awe-inspiring. The Bullet Cluster is the aftermath of a high-speed collision between two galaxy clusters, a cosmic crash so violent that it sent shockwaves through the fabric of space. But what made this collision so special wasn't the galaxies themselves. It was what happened to the invisible stuff between them. As the clusters collided, their galaxies passed through one another like ghosts, largely unaffected. However, the hot gas between the galaxies, which makes up most of the visible matter, was slowed and heated, creating a spectacular shockwave. Meanwhile, something invisible continued on its path, unaffected by the collision. This invisible substance was dark matter. The key to detecting dark matter in the bullet cluster came from a phenomenon called gravitational lensing. As light from distant galaxies passed through the cluster, it was bent by the immense gravity of both the visible matter and the dark matter. But because the dark matter didn't interact with the gas, it created a distinct separation between the visible and invisible components of the cluster. This separation was like a cosmic fingerprint, revealing the presence of dark matter in a way that was impossible to ignore. It was the first direct evidence that dark matter wasn't just a theoretical idea, it was real, and it was shaping the universe on a grand scale. The discovery of dark matter's role in the bullet cluster was a turning point in cosmology. It confirmed that dark matter isn't just a minor player in the universe's story, it's the dominant force, making up about 85% of all matter. Yet, despite its prevalence, dark matter remains one of the greatest mysteries in science. What is it made of? Is it a particle or something even more exotic? These are the questions that drive some of the most ambitious experiments in modern physics. Around the world, scientists are searching for dark matter particles using a variety of techniques. Deep underground, detectors like the Large Underground Xenon Experiment, or LUX, and the Xenon collaboration are waiting for the rare moment when a dark matter particle might interact with ordinary matter. In space, telescopes like the Fermi Gamma Ray Space Telescope are scanning the skies for signs of dark matter annihilations, where particles might collide and produce gamma rays. And at the Large Hadron Collider, physicists are smashing protons together at unimaginable speeds, hoping to create dark matter particles in the lab. So far, these efforts have yet to yield a definitive detection, but the search continues, driven by the tantalizing possibility of uncovering one of the universe's deepest secrets. The implications of dark matter go far beyond its role in galaxy clusters. It shapes the large-scale structure of the universe, guiding the formation of galaxies and the cosmic web. Without dark matter, the universe as we know it wouldn't exist. Yet, its very existence raises profound questions about the nature of reality. Is dark matter a single particle or a family of particles? Could it interact with forces we haven't yet discovered? And what does its dominance tell us about the universe's past and future? These are the questions that keep scientists up at night, pushing the boundaries of our knowledge. As we grapple with the mysteries of dark matter, we're reminded that the universe is far stranger and more complex than we can imagine. The bullet cluster gave us a glimpse of its invisible hand, but the full story is still waiting to be told. And as we continue to search for answers, we're driven by the same curiosity that has guided humanity's exploration of the cosmos for centuries. From the hidden depths of dark matter, we now turn our gaze to the farthest reaches of the universe where ancient light carries the echoes of the cosmos' earliest moments. This next discovery takes us to the edge of time itself, revealing the universe's most distant objects and the secrets they hold about the dawn of creation. At the edge of the observable universe, where the light of ancient stars stretches across billions of years, lies a galaxy so distant that it defies imagination. Known as GNZ 11, this faint smudge of light is the most distant galaxy ever observed, located an astonishing 13.4 billion light-years away. What does this mean? When we look at GNZ 11, we're seeing it as it was just 400 million years after the Big Bang, a time when the universe was still in its infancy, and the first stars and galaxies were beginning to ignite. This remarkable discovery isn't just a testament to human ingenuity, it's a window into the dawn of creation itself. Finding GNZ11 was no small feat. The galaxy is so far away that its light has been stretched into the infrared spectrum by the expansion of the universe, a phenomenon known as redshift. To detect this ancient light, astronomers relied on the Hubble Space Telescope, pushing its capabilities to the absolute limit. But even Hubble needed help. By combining its observations with data from the Keck Observatory in Hawaii, scientists were able to confirm GNZ11's record-breaking distance. This achievement didn't just break a record, it shattered our understanding of how quickly galaxies could form after the Big Bang. What makes GNZ11 so extraordinary is not just its distance but what it reveals about the early universe. This galaxy is surprisingly bright and massive for its age, suggesting that star formation in the early cosmos was more rapid and efficient than we once thought. It's as if the universe was in a hurry to build its first structures, lighting up the cosmic darkness with bursts of newborn stars. GNZ11 also contains elements heavier than hydrogen and helium, elements like carbon and oxygen that are essential for life. This means that even in the universe's earliest days, stars were already forging the building blocks of planets and perhaps life itself. Studying galaxies like GNZ11 comes with immense challenges. The farther we look into space, the fainter and more elusive these objects become. Detecting their light requires cutting-edge technology, precise observations, and a bit of cosmic luck. But the rewards are worth it. Each distant galaxy we find offers a snapshot of the universe at a different stage in its evolution, helping us piece together the story of how galaxies, stars, and planets came to be. GNZ11 is a critical piece of that puzzle, showing us that the universe was already bustling with activity long before our own galaxy, the Milky Way, even existed. As we peer deeper into the cosmos, the question arises, what's next? The James Webb Space Telescope, with its unparalleled sensitivity to infrared light, is poised to take us even further. It will allow us to study galaxies like GNZ11 in unprecedented detail, revealing their composition, structure, and even their motion. These observations will help us understand not just how galaxies form, but how they evolve over billions of years, shaping the universe into the rich, dynamic tapestry we see today. The discovery of GNZ11 is a reminder of how far we've come in our quest to understand the universe, and how much further we have to go. It's a testament to the power of curiosity, collaboration, and technology, showing us that even the faintest glimmers of light can illuminate the deepest mysteries of existence. And as we continue to explore the farthest reaches of space, we're driven by the same questions that have captivated humanity for centuries. How did it all begin? And what secrets does the cosmos still hold? From the ancient light of GNZ11, we now turn our attention to a discovery that reveals the universe's most violent events, a phenomenon so powerful that it can outshine entire galaxies and reshape the fabric of spacetime itself. This next discovery takes us into the heart of cosmic chaos, where the forces of creation and destruction collide in spectacular fashion. Imagine a light so bright that it outshines entire galaxies, a beacon so powerful that it can be seen from billions of light years away. This isn't the plot of a science fiction story, it's the reality of quasars, the most luminous objects in the universe. These cosmic powerhouses are fueled by supermassive black holes, devouring matter at an astonishing rate and releasing energy on a scale that defies comprehension. But quasars aren't just dazzling displays of cosmic power. They're also windows into the early universe, offering clues about how galaxies formed and evolved over billions of years. At the heart of every quasar lies a supermassive black hole, a gravitational monster millions or even billions of times more massive than our Sun. As matter spirals into the black hole, it forms an accretion disk, a swirling, superheated ring of gas and dust. The friction and magnetic forces within this disk generate immense amounts of energy, lighting up the surrounding space and creating the quasar's signature glow. In some cases, quasars emit more energy in a single second than our Sun will produce over its entire lifetime. It's a cosmic furnace burning brighter than anything else in the universe. But quasars aren't just about raw power, they're also cosmic time capsules. Because light takes time to travel across the universe, the light we see from distant quasars today left them billions of years ago. This means that when we observe a quasar, we're looking back in time, seeing the universe as it was when it was young. Quasars were far more common in the early universe, suggesting that the conditions for their formation, massive black holes and abundant gas, were more prevalent during this era. Studying these ancient objects helps us understand how galaxies grew and evolved, and how supermassive black holes came to reside at the centers of nearly every large galaxy. However, studying quasars is no easy task. These objects are incredibly distant, often located billions of light years away, and their immense brightness can overwhelm telescopes designed to capture faint light from other cosmic sources. To overcome these challenges, astronomers rely on advanced instruments like the Hubble Space Telescope and the Very Large Telescope in Chile, which can isolate the light from quasars and analyze their properties. By studying the spectrum of a quasar's light, scientists can determine its distance, composition, and even the environment around the black hole. These observations reveal not just the nature of quasars, but also the structure of the universe itself. One of the most intriguing aspects of quasars is their role as cosmic lighthouses. The light from quasars travels through vast stretches of space, passing through clouds of gas and dust that absorb certain wavelengths. By analyzing these absorption lines, astronomers can map the distribution of matter in the universe, tracing the cosmic web of galaxies and intergalactic gas. Quasars also help us study the universe's expansion, as their redshift provides a measure of how much the universe has stretched since the light left them. In this way, quasars are more than just spectacular objects, they're tools for understanding the cosmos on the grandest scales. Despite their brilliance, quasars are fleeting phenomena. Over time, as the black hole consumes the surrounding matter, the quasar's fuel runs out and its light fades. What remains is a quieter, more subdued galaxy with a dormant black hole at its center. This cycle of activity and dormancy is a reminder that the universe is constantly changing, with stars, galaxies, and even black holes evolving over billions of years. As we marvel at the brilliance of quasars, we're reminded of the incredible energy and complexity of the universe. These cosmic beacons not only illuminate the distant past, but also guide us toward new discoveries. And speaking of discoveries, our next exploration takes us into the realm of the universe's most mysterious signals that defy explanation and challenge our understanding of the cosmos. What could these enigmatic messages be telling us? The answers may lie in the most unexpected places. In August of 1977, a radio telescope in Ohio picked up something extraordinary, a signal so unusual that it left the astronomer who discovered it scrawling, "Wow." In the margins of the data printout, this brief, powerful burst of radio waves lasting just 72 seconds came from the direction of the constellation Sagittarius and has never been detected again. Known as the WOW signal, it remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. Was it a fleeting message from an alien civilization, or just an unusually strong burst of natural cosmic noise? Decades later, we still don't know for sure, but the WOW signal has become a symbol of humanity's quest to answer one of our biggest questions. Are we alone in the universe? The WOW signal wasn't just a random blip. It met all the criteria scientists had established for a potential alien signal. It was narrow in frequency, suggesting a deliberate transmission rather than a natural cosmic event. And it was incredibly strong, far more intense than the background noise of space. Yet, despite exhaustive efforts to find it again, the signal has never reappeared. This has led to countless theories, from the possibility of a one-time cosmic event to the idea that it was indeed a message from an advanced civilization, one that we simply missed. The mystery of the WOW signal has fueled both scientific curiosity and public imagination, becoming a cornerstone of the search for extraterrestrial intelligence, or SETI. SETI represents one of the most ambitious scientific endeavors of our time. For decades, researchers have scanned the skies for signals that might indicate the presence of intelligent life beyond Earth. Using powerful radio telescopes, they listen for patterns or anomalies that stand out against the natural noise of the universe. The challenge, however, is immense. The cosmos is filled with natural sources of radio waves, pulsars, quasars, and even the faint hum of the cosmic microwave background. Distinguishing a potential alien signal from these natural phenomena requires precision, patience, and a bit of luck. As one SETI scientist put it, it's like trying to hear a whisper in a hurricane. The search for extraterrestrial intelligence isn't just about technology, it's also about imagination and perseverance. Scientists like Jill Tarter, one of the pioneers of SETI, have dedicated their lives to this quest, driven by the belief that finding evidence of other intelligent beings would fundamentally change how we see ourselves and our place in the universe. Tarter once said, "We are not alone in the universe, we just don't know it yet." This optimism, coupled with rigorous scientific methods, has kept the search alive, even in the face of skepticism and limited funding. But the WOW signal and the broader efforts of SETI also raise deeper questions about how we define intelligence and what we're truly searching for. Are we looking for beings like us, capable of sending radio signals, or could life elsewhere communicate in ways we haven't even imagined? The universe is vast and the possibilities are endless. As we continue to explore, we're reminded that the search for extraterrestrial intelligence is as much about understanding ourselves as it is about finding others. While the WOW signal remains an enigma, it has left an indelible mark on our collective imagination. It's a reminder that the universe is full of surprises, and that even the briefest flicker of light or sound can spark a lifetime of curiosity. As we turn our attention from the mysterious signals of deep space, we shift our focus to another extreme, one that takes us to the very limits of temperature, where the universe reveals its most scorching and frigid secrets. What happens when matter is pushed to its breaking point, and how do these extremes shape the cosmos? The answers lie in the next chapter of our cosmic journey. Deep in the heart of the constellation Centaurus, a cosmic enigma defies the very notion of temperature itself. Known as the Boomerang Nebula, this ghostly cloud of gas and dust holds a record that seems almost impossible. It's the coldest natural place in the universe, with temperatures plummeting to just 1 degree above absolute zero. To put that into perspective, absolute zero is the lowest temperature possible, where all molecular motion theoretically stops. The Boomerang Nebula is so cold that even the faint afterglow of the Big Bang, the cosmic microwave background, feels warm by comparison. But how does such an extreme environment exist, and what can it teach us about the universe's most extreme conditions? This eerie nebula, located about 5,000 light-years from Earth, is a planetary nebula, a glowing shell of gas ejected by a dying star. What makes the Boomerang Nebula unique is the way its central star is expelling material at an astonishing rate, creating a rapid expansion of gas that cools as it spreads outward. Think of it like opening a can of compressed air. As the gas escapes, it expands and cools dramatically. In the case of the Boomerang Nebula, this expansion has created a frigid bubble of space that challenges our understanding of thermodynamics and the behavior of matter in extreme conditions. The extreme cold of the Boomerang Nebula also has profound implications for physics. At such low temperatures, matter behaves in ways that defy everyday intuition. Atoms and molecules slow down to a near standstill, and quantum effects normally hidden at higher temperatures begin to dominate. Studying environments like this allows scientists to test theories about how matter behaves under conditions that are impossible to replicate on Earth. It's like having a natural laboratory in space, where the universe itself conducts experiments we can only observe from afar. But the Boomerang Nebula isn't just a curiosity. It's a window into the life cycles of stars and the fate of our own sun. In about 5 billion years, our sun will undergo a similar transformation, shedding its outer layers and forming a planetary nebula. While it's unlikely to become as cold as the Boomerang Nebula, studying this extreme environment helps us understand the processes that shape the end stages of stellar evolution. It's a reminder that even in the coldest corners of the universe, there's a story to be told, a story of creation, destruction, and the delicate balance that governs the cosmos. As we marvel at the Boomerang Nebula's icy depths, we're reminded that the universe is a place of extremes, from the coldest regions to the hottest stars, from the faintest glimmers of light to the most violent explosions. Each discovery pushes the boundaries of what we thought was possible, challenging us to rethink our assumptions and explore new frontiers. And speaking of extremes, our next discovery takes us to the opposite end of the cosmic spectrum, where we'll encounter structures so vast and massive that they defy imagination. What could these colossal formations reveal about the universe's grand design? The answers lie in the largest structures ever observed, structures that stretch the limits of space and time. Stretching across the cosmos like an unimaginably vast tapestry, the Hercules-Corona Borealis Great Wall stands as the largest known structure in the universe. This colossal network of galaxies spans an astonishing 10 billion light-years, a distance so immense that it defies comprehension. To put it in perspective, if you could travel at the speed of light, a mind-boggling 671 million miles per hour, it would still take you 10 billion years to cross this structure. That's more than half the age of the universe itself. And yet, this enormous wall of galaxies isn't just a cosmic curiosity. It's a discovery that challenges some of the most fundamental principles of cosmology. The Hercules-Corona Borealis Great Wall was first identified in 2013, thanks to a survey of gamma-ray bursts, brief, intense flashes of energy that serve as cosmic beacons, marking the locations of distant galaxies. By mapping these bursts, astronomers noticed an unexpected pattern, a dense concentration of gamma-ray bursts that suggested the presence of an enormous structure. This wasn't just a cluster of galaxies or a supercluster, it was a wall, a filament of galaxies and dark matter that stretched across a significant portion of the observable universe. Its sheer size and scale immediately raised questions about how such a structure could exist within the framework of our current understanding of the cosmos. One of the key principles in cosmology is the cosmological principle, which states that, on large scales, the universe should appear roughly the same in all directions, a concept known as homogeneity. The discovery of the Hercules-Corona Borealis Great Wall seems to challenge this idea. How can the universe be homogeneous if structures of this size exist? This question has sparked intense debate among scientists, with some suggesting that the wall might be a statistical anomaly, while others argue that it could point to deeper, yet to be understood processes in the universe's evolution. Either way, the existence of such a massive structure forces us to rethink our assumptions about the large-scale structure of the cosmos. The implications of this discovery extend far beyond its size. The Hercules-Corona Borealis Great Wall offers a glimpse into the cosmic web, the intricate network of galaxies, gas, and dark matter that forms the backbone of the universe. By studying this wall, scientists hope to better understand how gravity has shaped the universe over billions of years, pulling matter into dense filaments and leaving vast voids in between. It's a cosmic puzzle, with each piece offering clues about the forces that govern the universe's growth and structure, but the story doesn't end here. The discovery of the Hercules-Corona Borealis Great Wall has also reignited the search for even larger structures. Could there be walls or filaments that dwarf even this one? And if so, what would that mean for our understanding of the universe's limits? These questions drive astronomers to push the boundaries of observation, using increasingly powerful telescopes and innovative techniques to map the cosmos in greater detail than ever before. Each new discovery brings us closer to understanding the grand design of the universe, and perhaps to uncovering structures that stretch the limits of what we thought was possible. As we marvel at the scale of the Hercules-Corona Borealis Great Wall, we're reminded that the universe is a place of endless wonder, where even the largest structures are just one piece of a much larger puzzle. And now, as we turn our attention from the vastness of cosmic walls, we shift our focus to something far smaller yet equally extraordinary: the universe's most energetic particles, which carry secrets about the most violent and mysterious events in the cosmos. From the colossal structures of the cosmos, we now shift our focus to the tiniest yet most energetic travelers in the universe: cosmic rays. These invisible particles, hurtling through space at nearly the speed of light, carry with them the secrets of some of the most extreme events in the cosmos. Among them, one particle stands out as a true cosmic anomaly: the Oh My God particle, an ultra-high-energy cosmic ray that defies expectations and challenges our understanding of physics. But what exactly are cosmic rays, and how do we detect something so small yet so powerful? The story begins with a mystery that has puzzled scientists for over a century. Cosmic rays are not rays at all, but high-energy particles, mostly protons, that race through space and occasionally collide with Earth's atmosphere. When they do, they create showers of secondary particles that cascade down to the surface, leaving behind faint traces of their journey. Detecting these particles requires incredibly sensitive instruments, often spread over vast areas to catch the rare events. One of the most famous detectors is the Pierre Auger Observatory in Argentina, a sprawling array of sensors covering more than 1,000 square miles. It's here, and at other observatories around the world, that scientists have captured evidence of cosmic rays with energies so high that they rival the power of a fast-pitched baseball, all packed into a single subatomic particle. The Oh My God particle, detected in 1991, is the most famous of these ultra-high-energy cosmic rays. Traveling at more than 99.9% the speed of light, it carried an energy of 50 joules, enough to power a light bulb for a fraction of a second, but concentrated into a single proton. To put that into perspective, this particle had the energy of a brick dropped from waist height, packed into something 1 trillion times smaller than a grain of sand. When scientists first calculated its energy, they were so stunned that one reportedly exclaimed, "Oh my God," and the name stuck. But how could a single particle achieve such incredible energy? And where did it come from? The origins of ultra-high-energy cosmic rays remain one of the greatest mysteries in astrophysics. These particles are thought to be accelerated by some of the universe's most violent events: supernova, active galactic nuclei, or even colliding galaxy clusters. Yet, even these extreme environments struggle to explain the sheer energy of particles like the Oh My God particle. Some theories suggest that they might come from beyond our galaxy, propelled by processes we don't yet understand. Others speculate about exotic sources, such as rapidly spinning neutron stars or the decay of supermassive dark matter particles. Whatever their origin, these particles are messengers from the most energetic corners of the universe, offering clues about the forces that shape it. Detecting these particles is no small feat. Because they're so rare, scientists rely on massive observatories like the Pierre Auger Observatory or the Telescope Array in Utah, which use networks of detectors to capture the fleeting showers of secondary particles created when cosmic rays hit the atmosphere. These observatories are like cosmic fishing nets, waiting patiently for the rare moment when an ultra-high-energy particle makes its presence known. And while the oh my god particle remains an outlier, each detection brings us closer to understanding the processes that can accelerate particles to such extraordinary speeds. The implications of cosmic rays extend far beyond their energy. By studying them, scientists gain insights into the behavior of matter and energy under extreme conditions, testing the limits of our understanding of particle physics. They also help us map the magnetic fields of our galaxy and beyond, as these fields bend the paths of cosmic rays, creating a complex web of particle trajectories. In this way, cosmic rays are not just particles, they're tools for exploring the universe's hidden architecture. As we ponder the mysteries of cosmic rays and the oh my god particle, we're reminded that the universe is filled with extremes from the smallest particles to the largest structures. And now, as we turn our gaze to another cosmic enigma, we find ourselves drawn to objects so strange and powerful that they defy explanation. What could these mysterious entities reveal about the nature of the universe? The answers lie in the shadowy realm of black holes, where the rules of physics as we know them begin to break down. Now, let's turn our attention to one of the most extreme and mysterious objects in the cosmos, magnetars. These are not your average neutron stars. Imagine a star so dense that a sugar cube-sized piece of it would weigh as much as a mountain. Now, add a magnetic field so strong it could strip the information off a credit card from halfway across the solar system. This is the mind-bending reality of magnetars, stellar remnants that defy our understanding of physics and push the boundaries of what we thought was possible in the universe. Magnetars are born from the explosive deaths of massive stars. When these stars collapse, their cores compress into neutron stars, but in some cases, the resulting object spins incredibly fast and generates a magnetic field trillions of times stronger than Earth. These magnetic fields are so intense that they can twist the very fabric of spacetime, creating ripples that propagate across the cosmos. But what truly sets magnetars apart are the cataclysmic events they produce: starquakes. Picture this: the crust of a neutron star, already under unimaginable pressure, suddenly cracks and shifts, releasing energy equivalent to a magnitude 32 earthquake. To put that in perspective, the most powerful earthquakes on Earth reach magnitudes of around 9. A starquake on a magnetar can unleash more energy in a fraction of a second than the sun emits in 100,000 years. These starquakes are not just cosmic curiosities, they are windows into the physics of extreme environments. The energy released during a starquake can produce bursts of gamma rays, X-rays, and even gravitational waves, giving scientists a rare opportunity to study the behavior of matter under conditions that are impossible to replicate on Earth. For instance, the intense magnetic fields of magnetars can create exotic states of matter, where particles behave in ways that challenge our current understanding of quantum mechanics. Studying these phenomena helps us refine our theories about the fundamental forces that govern the universe. But magnetars don't just push the limits of physics, they also have real-world implications for our understanding of the cosmos. Their powerful magnetic fields can influence the surrounding space, accelerating particles to near light speeds and creating jets of radiation that light up the galaxy. Some scientists even speculate that magnetars could be the source of fast radio bursts, those mysterious millisecond-long signals that have puzzled astronomers for years. By studying magnetars, we're not just exploring the lives of individual stars, we're piecing together the broader story of how the universe's most energetic events shape the cosmos. The existence of magnetars also raises fascinating questions about the fate of neutron stars. Are all neutron stars born with such extreme magnetic fields, or do magnetars represent a rare and unique class of objects? And what happens to a magnetar as it ages? Over time, their magnetic fields decay and their rotation slows, but even in their quieter states, these objects remain some of the most intriguing and enigmatic in the universe. They remind us that the cosmos is full of extremes, from the coldest regions to the hottest stars, from the faintest glimmers of light to the most violent explosions. As we marvel at the power and mystery of magnetars, we're reminded that the universe is a place of constant discovery, where even the most bizarre objects can teach us something profound. And speaking of cosmic signals, our next discovery takes us to the farthest reaches of space, where ancient light carries the whispers of the universe's earliest moments. What secrets do these distant signals hold, and how can they help us unravel the story of the cosmos? The answers lie in the faint afterglow of the Big Bang itself. Imagine a time when the universe was cloaked in darkness, long before galaxies, stars, or even the faintest glimmers of light existed. This was the era of the cosmic dawn, a pivotal moment in the history of the cosmos when the first stars ignited, piercing the blackness and setting the stage for everything that would follow. These ancient stars, born from the simplest elements, hydrogen and helium, were unlike anything we see today. They were massive, blazing infernos that burned brightly but briefly, seeding the universe with heavier elements and lighting the way for the galaxies that would one day form. Studying this era is like peering into the universe's infancy, offering us a glimpse of its earliest moments and the forces that shaped its evolution. But how do we observe something so distant, so faint, and so ancient? The light from the cosmic dawn has traveled for over 13 billion years to reach us, stretched and dimmed by the expansion of the universe into faint radio waves. These signals, known as the 21-centimeter line, are emitted by neutral hydrogen atoms, the very building blocks of the early cosmos. By capturing this ancient light, astronomers can map the distribution of gas in the early universe, tracing the formation of the first stars and galaxies. It's like listening to a whisper from the dawn of time, a faint echo of the universe's first steps. The challenge, however, is immense. The signals from the cosmic dawn are incredibly faint, buried beneath layers of interference from our own galaxy and even human-made radio signals. To detect them, scientists have built specialized instruments like the Hydrogen Epoch of Reionization Array, or HERA, and the planned Square Kilometer Array, which will be the largest radio telescope ever constructed. These observatories are designed to filter out the noise and focus on the faint whispers of the early universe. But even with such advanced technology, the task is akin to trying to hear a single instrument in a symphony while standing miles away. What makes this era so crucial to our understanding of the cosmos? The cosmic dawn marks the transition from a dark, featureless universe to one filled with light and structure. The first stars not only illuminated the cosmos but also triggered a process called reionization, where their intense radiation stripped electrons from hydrogen atoms, transforming the universe from an opaque fog into the transparent expanse we see today. This period set the stage for the formation of galaxies, including our own Milky Way, and laid the groundwork for the complex web of cosmic structures that define the universe today. By studying the cosmic dawn, we're uncovering the origins of the universe itself, how it went from a simple, uniform state to the rich tapestry of galaxies, stars, and planets we observe now. The implications of this discovery extend far beyond astronomy. The cosmic dawn challenges us to rethink our understanding of the universe's evolution and the forces that drive it. It also raises profound questions about our place in the cosmos. Were the conditions that led to the first stars unique, or are they part of a larger pattern that could repeat in other universes? And what can the cosmic dawn tell us about the nature of dark matter and dark energy, the mysterious forces that dominate the universe? These are the questions that drive astronomers to push the boundaries of observation and technology, searching for answers in the faintest signals from the past. As we peer into the cosmic dawn, we're reminded that the universe is a story still being written, with each discovery revealing a new chapter in its history. And now, as we turn our gaze from the first stars to the forces that shape the cosmos on the grandest scales, we prepare to explore the universe's most enigmatic influence, a force so pervasive yet so mysterious that it defies comprehension. What could this force be, and how does it govern the fate of the universe? The answers lie in the shadowy realm of dark matter and dark energy, where the cosmos holds its deepest secrets. As we've journeyed through the cosmos, uncovering black holes, pulsars, and the faint whispers of the first stars, one mystery has loomed larger than all the rest, a force so pervasive that it shapes the very fate of the universe, yet so elusive that it defies detection. This is dark energy, the enigmatic force driving the universe's accelerating expansion. It's a discovery that has reshaped our understanding of the cosmos, revealing a universe far stranger and more dynamic than we ever imagined. But what is dark energy, and how do we know it exists when we can't see it, touch it, or even fully comprehend it? The answers lie in the subtle clues scattered across the fabric of space itself. The story of dark energy begins with a paradox. In the late 1990s, astronomers studying distant supernova made a startling observation. The universe wasn't just expanding, it was doing so at an ever-increasing rate. This was a shock to the scientific community. For decades, the prevailing view had been that the universe's expansion, set in motion by the Big Bang, would gradually slow over time due to the pull of gravity. Instead, the opposite was happening. Galaxies were racing away from each other faster and faster, as if some invisible force were pushing them apart. This force, now known as dark energy, made up about 70% of the universe's total energy content. Yet its nature remained a mystery. So how do we know dark energy is real if we can't directly observe it? The evidence comes from multiple lines of inquiry. Observations of distant supernova provided the first clues, but they were soon supported by measurements of the cosmic microwave background, the faint afterglow of the Big Bang. These measurements revealed the universe's overall geometry and energy density, confirming that dark energy was not only real but also the dominant force shaping the cosmos. More recently, large-scale surveys of galaxy distribution have further solidified the case, showing how dark energy influences the growth of cosmic structures over billions of years. But understanding what dark energy actually is remains one of the greatest challenges in modern physics. Some theories suggest it's a property of space itself, a cosmic springiness that Einstein once called the cosmological constant. Others propose that dark energy could be a new kind of field or particle, something entirely beyond our current understanding. The truth is, we simply don't know yet. Dark energy doesn't interact with light or matter in any way we can detect, making it incredibly difficult to study. It's like trying to measure the wind by watching the leaves rustle. We can see its effects, but the force itself remains invisible. The implications of dark energy are profound. If the universe's expansion continues to accelerate, it could lead to a future where galaxies drift so far apart that the night sky becomes a vast, empty void. Stars will burn out, and over trillions of years, the universe may grow cold and dark, a stark contrast to earlier theories that predicted a fiery collapse. This scenario, known as the Big Freeze, is just one possible fate for the cosmos, but it underscores the importance of understanding dark energy. It's not just a scientific curiosity, it's a force that could determine the ultimate destiny of everything we know. Efforts to unravel the mystery of dark energy are ongoing, with astronomers and physicists using every tool at their disposal. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map the universe's expansion in unprecedented detail, searching for subtle changes that could reveal dark energy's true nature. Meanwhile, particle physicists are exploring exotic theories, from extra dimensions to new forms of matter, hoping to uncover clues in the subatomic realm. It's a global effort driven by the shared belief that solving this mystery could revolutionize our understanding of the universe. Dark energy reminds us that the cosmos is full of surprises, often hiding in plain sight. It's a force that connects the largest scales of the universe to the smallest, shaping everything from the motion of galaxies to the behavior of particles. And while we may not yet have all the answers, the pursuit of this mystery is a testament to humanity's unquenchable curiosity and our relentless drive to explore the unknown. As we continue to probe the depths of space, we're reminded that the universe is far stranger and more wondrous than we ever imagined, and that the greatest discoveries are still waiting to be made. With this final discovery, we've come full circle in our exploration of the cosmos, from the ripples of space-time to the shadowy realms of dark energy. Each revelation has peeled back another layer of the universe's infinite complexity, challenging our assumptions and expanding our understanding. Together, these 25 groundbreaking discoveries remind us that the universe is not just a collection of stars and planets, but a dynamic, ever-evolving story, one that we are only just beginning to understand. And as we look to the future, we can't help but wonder what other mysteries lie hidden in the vast expanse of space, waiting to be uncovered. The journey of discovery is far from over, and the cosmos still holds countless secrets for us to explore.